So let's take a look at how we quickly do this, and then we get into our problem. So this first one was about pH. You're like, well, how was I supposed to be able to calculate that without a calculator? This is what I basically did. Was I said, well, if pH is 11.5, it wants to know OH. OH is 2.5. This is how and you don't know this, you need to know this. If pH was 2 or pH was only 3, 10 to the negative second or 10 to the negative third would be 0.01 or 0.001. So it gave me a reference. Okay, it's in between those and the idea, so I'm just kind of thinking about it. So now I can kind of take a look at which answer would be the closest. And what I do is I come up with the idea that it's letter B because of just the overall exponent and where the range is. I don't know if that makes sense. They're not going to ask for such a specific value that the different options will not let you figure that out. So again, 10 to the negative whole number will just move you that many decimal places, right? So if you didn't get that one right, whenever you get a pH problem, you got to remember, again, throughout the whole multiple choice section, there's only going to be a handful of problems that are going to be calculations that are going to be a little tricky. So that's what I want to kind of go through to help you out. This one, what mass of Cu would be produced if 0.4 moles of Cu2O was reduced completely with excess H2? All right, that can seem really overwhelming and confusing. The first thing is I need an equation. So it says that this would be produced if that reacts with that. So this might show up all together, and if it doesn't, sorry, shoot. So just kind of check this out. I wrote this down. I organized my information really quickly. I said I had 0.4 here, and I want grams of that. I didn't do any units more than I needed. I went from moles to grams. So ratio, mole ratio, and then that's what actually it weighs. So I just kind of figured out that it's approximately 0.8 times 63.5. I figured it's around 50. Like it's going to be less than 63 because I'm taking about 80% of that. So I figured out it's going to be 51. And there's a huge leap there. It's probably not in this range. That's another guess. If you have literally no idea and you know you have to calculate it, numbers that are quite close to each other, it's a good shot it's probably not an answer because you're having to round. And you may not be able to, now that you could come up with 1,000 examples of where that could fall into place. I get it. But if you have no idea, an educated guess would be something where it would be one of these three, I would guess. That would be probably what I would say. Or maybe really low. It all depends on what your numbers are. Last one. This one I thought was hard because it's hard to understand it. It says you have a 1.25 gram sample of limestone that was dissolved, 0.44 grams of CO2 was generated. If the rock contained no carbonate other than that, so limestone, again, limestone's unique because it has different kinds of carbonates in it to make it up. What was the percent of CaCO3 by mass in the limestone? Again, I might have the whole answer show up, and if it does, that's okay. This is what I figured out. The whole thing weighs 1.25. It made 0.44 grams of CO2. If you didn't get the equation, well, yeah, that's going to be harder. But let me just show you the math. Today I'm trying to show you how I figure stuff out, doing this quickly without a calculator. I'm trying to figure out how much I made of that. Like how much was resulting of the CaCO3 from how much carbon dioxide was made. So this is not uncommon. 0.44, carbon dioxide is 44 grams. What's 0.44 divided by 44? What is it? 0.01. 0.01. And then, amazingly enough, this weighs 100 grams. Well, you didn't have a calculator. Okay, 40 plus 12 plus 16 plus 16 plus 16. Yes, that's a little bit more, but you'd have to figure it all out. It's 100. So 100 divided by 0.001, because of that relationship there, you get 1 gram. So regardless if you don't understand the question, it was hard. I looked this up. It was a very low percentage of people that year that actually did well on that. This is an actual question from years ago. Then I found out that it actually produced 1 gram. So 1 gram of the limestone was CaCO3 of the total limestone. So that's 80%. And if you're like, I don't get that either, turn it into fractions then. This is 4/5. Right? There's 4.25 or 5.25s and 1.25s, and there's 4 of those now. Okay? So, regardless if you understand the question completely, this exercise was meant to help you with the math and just show, hey, you can calculate things, you can round. And I know we did the first two. PV equals nRT is a huge one. It's going to come up to make 0.08 as a point one, and move forward. Okay? So, all right, we are going to work on problems today. So if you have your packets, out, we are going to go through everything that we haven't hit yet. We're going to be totally up to date except for 4 through 6. I still got to get a plan for that. So, oh no. What?
In 1 sec, we'll be off. So we're going to start with chapter 14 and 16 that we were supposed to have done today. I saw some people had some questions on there as well, which is exactly what and why we need to go over it. I just made one error I need to just fix. Sorry.
That's Justin.
All right. All right, here we go. So these are really important to have understandings of it. And again, we're always guaranteed equilibrium problems. So these are really important equilibrium problems to have an understanding from beginning to end. So you have a table right here, and we have to answer a bunch of questions in the beginning about it. Which of the two acids is stronger, HOCl or HOBr? Justify your answers in terms of Ka. We've been learning that the larger the K, the more it moves to the right. So hopefully we would agree then that HOCl is the stronger acid because the K value is greater. And it says justify your answer in terms of Ka. So you have to make sure you do that. Draw a complete Lewis electron dot diagram for the acid that you identified. So whichever one you said, you got to make sure it's going to be very similar. So if you don't have the dots, everything's basically a point here. In the next section, we'll do points. If you didn't do dots, that's wrong.
Wait, why wouldn't there be a dot?
Oh, 2 more dots right there. Thank you, Rory.
Yeah, you're right.
You're fine. Yeah, okay, good question by Kevin. So he picked let's just say, I don't know if you did or not, if you picked HOBr here, as long as you drew the HOBr here, you get the point for that because it says, it's basically saying whatever you use from that one. So yeah. Hypoiodous acid has a formula of HOI. Predict whether HOI is a stronger or weaker acid than the acid you identified in part AI. Justify your prediction in terms of chemical body. This is hard. And this is a great one to go over. This is actually, literally this part right here is why I picked this problem. Okay. What makes an acid strong or weak? What is it giving up? An H. So strong acid freely gives up an H, right? All of it. Take it, please. Take all my H's. Strong acid. A weak acid is holding on to their H's. So when you are asked about strength, you have to look at it in terms of how strong is that H being held on. Okay? Well, if energy and focus is being pulled away from that bond gets weaker. So what I'm trying to say is the stronger this is, and the stronger the pull over here, and the electrons are being pulled over, how does that affect my H? Okay, that's what you have to think about, because that's all you can go off of. Because in this case, I hope that you notice, is that whichever one I pick, which I'm going to pick this one, that OH is still OH, so it's the OCl versus the OI, okay? So, this is a stronger bond because of the electronegativity, or stronger force, O and Cl, right? That's a stronger electronegativity, it's a Cl versus the I. I has a lower electronegativity. So what actually happens, I hope this is going to make some sense, is that, and you could, I see how you can flip this. Oh, it's stronger, so it's pulling it all over and it's going to hold on to it stronger. It's still the same bond, O and H. What's happening is that the Cl is going to take more of the electrons away from O, so O has less influence on the H than this O, because the I isn't pulling the electrons as far, so it has more electrons to share and to hold and not to let it go. So the stronger electronegativity difference between the OCl and the OI causing the H to dissociate easier. So the weaker the acid, H is held on tighter.
Could you look at just the chart and say that, like, as your halogens got bigger, your Ka value got smaller?
I mean, that's an interesting trend, right? Because it's Cl and then Br and then it'd be I.
Yeah, like the atomic radius.
I'd be interested to see, this is the one question I'd have for that, Kevin, is that it tries to make you speak specifically on terms of chemical bonding. So, but if you didn't know and you realize, well, it's going to be weaker, you could just try to then sell that by saying, well, as the halogen gets larger, the bond weakens or strengthens. I mean, you'd have to commit somehow though, and you may commit the wrong way, but it's a great observation. Just the other thing I guess I would just say to you again is, usually problems in AP, there's a similar part and there's a part that is different all the time. You use the similarities and you compare them to the differences. And usually what you do is you focus on the differences, and that affects what's happening that is similar in between them. So anyway, that's hard. I think that is really difficult. I think it's important to understand. Again, the stronger the acid, the more it actually lets NH go. It seems counterintuitive, but it makes sense with what we talked about with acids. Okay, keep moving forward. Write the reaction, or the equation for the reaction that occurs between hypochlorous acid and water. There's two options. You can draw either one. Obviously, if I have these flipped, it's okay. So acids, we can always not write the HOH. Why? Because we can make H3O plus as H plus. So if you wrote either one of those, you're right. That's just the point. So did you write one of them? You never had to write two. It didn't ask to. You do not need to write two. But hopefully that makes some sense. So that really is it's going to help you with the problems, but independent of what you just did before. All right, C. So now you got an amount. 1.2 molar of that is prepared by dissolving NaOCl in water. The hydrolysis reaction is that. Sorry. Just want to zoom in a little bit more. Write the equilibrium constant expression for the hydrolysis. Just the expression. So I hope that clicks. I hope that makes sense, right? I don't write a liquid. So I have AQ, I have AQ. That should be points. We should have that. We should have those points. Now, it did not say this. How do I know it's a KB? OH minus. OH minus. You have to commit to a K. I believe that you may not get all the points if you don't write the KB. You just wrote K. I don't know that for a fact. But for sure don't include the water. But that's a KB because there's an OH. And there's an H plus, and that would be a Ka. Okay? Double I, calculate the value of the equilibrium constant for the hydrolysis. All right. So, if I'm going to calculate this, that means I need to know all of these. Okay? So how do I know all that? What do I know? What information do I have? Well, what I have is no information. Sorry, I got ahead of myself. I was about to say, I don't have information yet of this stuff. I have only a piece of that. If I only have a piece, I would need to know K. Well, this was, I gotta find it. Is that from the, that's gotta be it. That's right, okay, I was gonna say, yeah, right. The HOCl, that's from the beginning. So you do have a Ka. Clearly the partnership, this reaction is based in terms of the OCl minus. So if you have a conjugate pair, then you can do the Ka, Kb, Kw. Sorry, I was getting on myself. I know it's coming up right here. So, if you feel like you don't have enough information, then you got to kind of realize, okay, what else do I have? What is this about? What is tricky about this problem is it's not going out of its way to kind of declare, like, this is going to be my base. Like, that is what's happening, and you're going to compare it to the acid. So, if you didn't notice that, please understand whenever we're doing Kas and Kbs, if they jump back and forth, that could potentially be happening. All right, what is the OH value? I have only 1.2 molar. This is a salt. This breaks up, and I have that. So I have 1.2 of that. I have a K value. I have a value initially. So I have 1.2 of that. I started an icebox, and for some of you, maybe you recognize it right away. If you didn't, oh wait, I don't have any amounts of anything else. Wait, I have an initial, and I don't have other amounts. That's x squared over initial minus x. And I know this is getting cut off, but I have 3.4 times 10 to the negative 7. Whatever number you had here, you actually could use it. So if you did this wrong, it would still be okay. It's not double jeopardy. X squared over 1.2 times minus x. That's going to be my OH minus. It would be 6.4 times 10 to the negative 4th. So if you didn't recognize that is initial minus x, or that I should do an icebox, just keep that in mind, please. If you have an equation and they've given you one, and then they just give you an amount that is started off, you're probably going to need that at some point. You're going to need to do that at some point. So that's actually 2 points, one for the setup, one for the answer. How many more? Oh, is this it? A buffer solution is prepared by dissolving some solid NaOCl in a solution of HOCl at 298. The pH of the buffer solution is determined to be that. Okay. In an icebox, ICE, what does that affect? I, C, or E if I put it in an icebox? Like eventually? That's going to be an E. Now you can't put it like that. You got to take 10 to the negative that. But that's an E. That pH always reflects equilibrium. I think it's important to keep on the forefront. Calculate the value of H3O plus in the buffer solution. Where do I get that from? Here. That's pH. So I just take 10 to the negative that. Right? I hope that there's certain parts and problems that are really difficult, and then what's nice, don't assume it just gets harder. And if we didn't get that, I'm not saying one thing or another about, oh, well, you should have gotten that. I'm just saying that that is much more simplistic than even doing an icebox. You just need to recognize it. 3.3 times 10 to the negative 7. All right. Now, there's some more work here. Indicate which of these two is present in a higher concentration in the buffer solution. This is hard. You can do this 2 ways. Let me show you. And it's just going to all show. So, boom.
Wait, would that give you
sorry.
Would that give you the Ka or the Ka formula?
No, that's pH. So pH equals negative log of H plus. So if I take 10 to the negative pH, I get H plus. So the blue one is what I would do. This is what the AP answer key did. I like the blue. So let me just talk this through with you. It's confusing. Like, I don't even know what I'm finding. It's a ratio. That was the trick of this. Which one do I have more of? It's a ratio. So I just sat back for a second. I'm like, wait a minute. There should have been decimal there. I have pH. I know a K value. And then they're asking for a conjugate pair. Those are things that are in the Henderson-Hasselbalch equation. I could actually solve for this, and check this out. This is a ratio. Well, just simply by writing this, it tells me, because this number is here, that there's more of that because of the values, right? Just because of the answer. Well, how do you know? Well, because it's less than 1. So there's more of this than that. They did it much differently. They set it in the K, if you're like, no, I like this one. They put it in the Ka expression, and then they basically said, well, here's the Ka, and this is how much H plus I have. So then they rearranged this, and they divided this over the other side. It's actually shorter, and then that math equaled that. So just basically, I know it looks like I just flipped these around. I just divided it under, and either way, the ratio is saying that I have less. So let me just tell you that this happens once in a while. If they ever compare about 2 things, and they don't want a number, they just say, which one do you have more of? Ask yourself, is that a ratio somewhere? Like, is that in some sort of either an equation or an expression that instead of plugging in the actual values, I could just get a number that's reflecting that relationship? It happens. It's kind of a mathematical trick, but it would work, okay? So I don't remember, but I'm assuming that is definitely worth 2 points, just the amount of work. Okay, let's jump to the other one, I think, right? Again, the equilibrium, I cannot overemphasize how important these are going to be. Answer the following questions about the solubility of the reactions and the reactions of the ionic compounds MOH2 and MCO3, where M represents an unidentified metal. A, identify the charge of M ion in the ionic compounds above. I hope we all said it was +2. Do not just write a 2. Charges have charges, plus and negative. So, right, carbonate is a -2 and OH is a -1, so that would have crossed there and it didn't cross there, so that makes sense. B, saturated solution of the hydroxide has a pH of 9.15. I, calculate the molar concentration of OH in the saturated solution. The molar concentration of OH. Well, if that's pH, I can get OH, and then I can get, POH, and then I can get to OH minus.
So in doing that, are we assuming that MOH2 is a strong base?
Yes. That's a good question. I'm going to say yes. Or else you need K's, right, and things. Yeah, right. Just seeing if there's anything else that's said. I don't know. Couple of quick things on this. You guys, if it started with this and it gave you an OH concentration, it's doubled before you get the pH. But it already gave you the pH, so you don't have to worry about it. Like, that is the OH concentration then. Like, that's the overall OH concentration. So whatever the pH is, that's the resulting amount of OH that's present. I know some people could get a little confused by that. You don't double, I'll just say this, you don't double the POH. Like 4.85, oh, there's 2 of them, times 2. No. And when you get the final amount of OH, you don't double that because that was the resulting amount that created that in the first place. All right, now this is where, please open your brains because KSP we don't cover as much, and this is, it gets tricky. I was going through this last night and I could totally see people not understanding how to do all this. First, hopefully we did this right. Write the solubility product constant expression for MOH2. First off, that's KSP. You're like, oh my gosh, I didn't even know what they were asking. This is what it should have looked like. Remember, it's the compound and then it dissolves into its ions. Which one do I know is on the left or the right? The ions are always on the right. We say it's a solid, then does it dissolve? So that's what it needs to look like. Keep in mind that you need an exponent when you have more than one. Okay, calculate the value of the solubility product constant, KSP. Okay, if I'm solving for that, that means I must know this. So I broke this down. The answer key does not break it down as much as I did. And just slow down with me here. I wrote the equation. And basically I said, okay, it doesn't dissolve. Where's that from? That's from saying that's how much OH I have. I'm hoping this is going to make sense here. I filled it in. I took my time. This would be plus 2x. This would be plus x. So then I do simple algebra and say, well, if this is 2x, x would be that because I just simply divided this by 2. Right? Because this was 2 times x equals that. So this is just x. Well, check out, please note my numbers. And I put that in blue because that's the secret, that's the hidden number, the one that hasn't been determined yet. I plug those in right here. These are put into my expression, right, just from the end of my icebox. They didn't do an icebox at all. They had all this, they just multiply it by half and they jumped right into it. It's not very descriptive. And for us to learn and make sure that we're understanding this, you need to understand where these are coming from. Okay, and then I squared it, and then I got a KSP. That,
The 7 times 10 to the -6.
that's the x. Whereas x, well, this was 2x equals that. So what I did is I divided this value by 2 to get what x was.
How did you know that?
Because I set up the icebox. I knew this was already from here because it says OH.
Okay.
And all pHs are about equilibrium, right? That's important. pH goes to the equilibrium line, always. So iceboxes help. Don't be too full of yourself to go, I got it. Organize it. Even if you start it and go, oh, yep, that's what I thought it was. It just confirms you and it feels good that you know you're going in the right direction. Even if you just started an icebox. Oh, I got it. It helps. Okay, so we're going to need that. In the next couple from my memory of last night, these were tricky, and it's good to see. So I'm moving on, I hope you have it. So for the metal carbonate, the value of the solubility product is 7.4 times 10 to the negative 14. This is a big question, and don't let this rattle your whole basis of AP Chem. On the basis of this information, it results in part B, which compound? The hydroxide of the carbonate has a greater molar solubility. Okay, basically what I need to figure out what the molar solubility is. What that means is it's the value that equals, it's the single ion that is the same as saying the overall molar solubility, like how much can dissolve. Let me say in a different way. If you have CaCl2 and you say that it's 2 molar, CaCl2, the molarity of Ca would be 2, the molarity of Cl would be 4, right? 2 and 2. The molar solubility of CaCl2 is still 2 because it reflects the one that is the 1-to-1. Like the overall compound is 2 molar, CaCl2. Each ion might have more. So this is the molar solubility right now of this. Okay, it's how much can dissolve. It's the maximum amount that can dissolve. We always use the single molarity. Okay? I don't know if that makes sense, but like AlCl3, if it's 2 molar for the whole compound, I don't talk about the molarity of the Cl when I talk about all of it. I talk about just it's 2 molar. It's not 6 molar. So let me show you. This is tricky. That was just from before. This is how I figured this one out. They gave me the KSP, so check it out. This equals these two things. So does that not equal basically x squared? Right? So if I take out one of those, that's what each of these, this value and this value, if I did my math right, equals KSP. So the molar solubility, meaning the maximum amount that can dissolve of the entire compound, is 2.7 times 10 to the negative 7. Thought this was the hardest problem just because of understanding. So this is the maximum amount that can dissolve for the hydroxide. This is the maximum amount that can dissolve for the carbonate. Even if you don't understand all the math, you do need to understand this relationship for sure. I hope it makes sense. This is a larger number, so more can dissolve. So it's a higher molar solubility. Molar solubility is a fancy way of just saying solubility, the maximum amount that can dissolve, maximum amount of particles that are in the solution. So the hydroxide has the greater molar solubility. I don't know if that can help us or not, but I'd like to think it did. So, again, they told us this already. And then I just said, okay, it equals x times x. Right? 0, 0, and then it'd be plus x's, so it'd be x squared. So you just take square root, and you would get that. Because each of these values would be in here. And these are both 1 to 1. Okay. Kind of finishing it up. You get a new equation. That was actually given to us. Sample of it is placed in a previously evacuated container and allowed to come in equilibrium. Some solid NCO3 remains in the container. The value of Kp for the reaction is 0.0012. Okay, this is not nearly as tricky as it looked in the beginning when you're reading this. Write the equilibrium constant for Kp. Kp's only deal with gases. Okay? There's only one gas. So it should look like that. That's it. Determine the pressure in ATM of CO2 in the container at equilibrium. This is the Kp. If that equals Kp, what's the pressure of CO2 at equilibrium? 0.0012. How do you know that's at equilibrium? Because a K is equilibrium. Right?
You're running radar out there.
Oh, I was going to say it might be too. Get him in here. Indicate whether the value of G for the reaction is positive, negative, or 0. Justify your answer. Okay, so you sit back and go, I don't know. Reminder, every time something comes up with G, I'm looking at my yellow sheet. I'm looking at my yellow sheet, and what is the only thing, if I start looking through my yellow sheet that they gave me? They gave me K. So this is how I did this. And you could just screw around with numbers. I mean, actually, you could put the whole thing in. I didn't. You could put 423 in here, you put your R value in there, and then you put your K. You could get the whole number. I didn't even think about that. I just looked at what this is going to do. I could have punched the whole thing in. Because this is less than 1, when you take negative natural log of that, it's going to be a negative value. So negative times a negative Change G is going to be positive.
If we collect all of the stuff, then would that count as justifying our answer?
Yeah. Is that spontaneous? It's not a question, but no, it's not. So this reaction is not favored. That's what that means. Okay. G is the ultimate guide. Is that it for that one? Is that the last question? Okay. We're going to fly through a couple other ones. So again, tough. I know we're reviewing it multiple times, but hopefully that helps. If you were not able to make it last night, we went through 3 problems as well. Hopefully those helped a little as we go. We will have another one soon, but.
Does that whole change in G equals 0 if the system's at equilibrium thing count, or is that talking about?
That's if you're at a phase change. It's at a phase change.
Oh, is it?
Okay, that one we're gonna skip this one for now, 2001. So what I'd like you to do, find, we're going to chapters 10, 11, the things that we did yesterday. We're gonna fly through the answers of these and you can see how they're scored, okay? And I just want you to see them. So hopefully you had done them all already. That's kind of the point. If you're sitting there scurrying, writing it all, you can correct, but if you're starting from scratch, it's pretty much impossible. I don't know which one, help me out, which one is this one? Chapter 10?
Yeah.
Second chapter 10, I think. We'll go over this one later. To be honest, I forgot to put the answer. I can do this really fast just to say it. I'm just going to verbally say this, so this is going to take like a minute. Even though I like these kind, because these are fast. So what you're supposed to do is talk about both substances. So even though NH3 and CH4 have similar molecular masses, NH3 has a much higher normal boiling point than CH3. Why? NH3 has H bonding. CH3 does not. So it's higher IMFs. Okay? And I'm going to do this really fast. This has no other answers. I'm sorry. Kevin, I think this is the one you came, maybe. At the same pressure, this one's a gas, this one's a liquid. Why? They're both LDs. This is what I like to do. I like to say the things that are similar if I can, or say the things that are different, but you have to talk about each. So what I'm saying is these are both LDs. Well, clearly, which one has the stronger IMF, though? Because this is a gas, this is a liquid. The same condition. Which one's stronger? The hexane, because it's still a liquid. It's still stuck together. There's stickiness. So, what did we learn about LDs? How do they get stronger than another LD? When the compound is larger or bigger size. The larger the size, the larger the LD. This is a larger electron cloud, stronger LD. That's why it's still a liquid.
For H bonding, is it only when H's are bonded together?
No, when H is bonded to F, O, or N, you got to have fun with H bonding. Si melts at a higher temperature, whoa, crazy, than Cl2. This doesn't come up much, and I know we didn't, this is the one thing we didn't talk about all that much. This is an LD. Kevin, did you find out what this was? Starts with an N. Network solid. Carbons and silicon, if they're by themselves, it makes a crazy strong, diamonds, all right, quartz, crazy strong. I mean, a network itself, networks are designed to be strong. So that's a network solid. They're purposely trying to show you like, wow, look at that's a mind blow. So network solids are much stronger bonds or forces or LD or IMFs than.
Can you tell me what if it's more of an atom?
You'd have to say network solid though. If you didn't, unfortunately, you missed that one. And then the last one, MgO melts at a much higher temp than NaF. Guys, you may not remember this, and this is actually the reason why I did want to quickly go over this one again. I don't know if you remember this. It's called Coulomb's law. It was charge over size. Charge over size. Something smaller, it bonds stronger to make a crystal lattice. The other thing on the top was charge. The greater the charge, the more attraction. So this is a 2 plus and a 2 minus. This is a 1 plus and a 1 minus. So these have greater charge than that. So that's why it's a stronger, it's showing that it has a stronger bond. So it's due to the charge, greater charge in the MgO than in the NaF. The size doesn't matter that much in that one.
Does the having a stronger dipole matter as much?
Not for this one. This one actually is truly going to crystal lattice, and it's talking about the size, the charge over the size. So if you ever see a salt and they're comparing two different salts, you got to try to. That one's kind of hard to pull out of, but we'll continue to talk about. It's about charge or size. So if it's the same charge, then you got to go size. If they're relatively the same size, then you got to look at charge.
Are dipole, dipole, H bond, and London forces only in covalently bonded substances?
Yes.
And everything else is ionic? like.
More or less, yes. So yeah, covalent compounds are the ones that have the H bond dipoles and Londons. Everything technically has a London. And then once you get into ionic, then you're talking about the difference between charges and things. Okay, let's quickly talk about this one now. Sorry. Explain why, and we'll see as far as we get. H for the formation of I2 gas from I2 solid is larger than the Br gas to Br liquid. Don't write it all down. I just want to show you points. Two reasons can be given. I'll just read a little bit of this, but they're both London. They're definitely both London. But, I mean, to be honest, this is the greater one. Why? Because you're going through two phase changes. Right? You're going through two phase changes. Versus one. You have to absorb a lot more energy to slow down, or to gain energy to get to a gas from a solid than from a liquid to a gas. And that's truly what it is. That's the big one there. I mean, there are some other things you can talk about. Iodine is also larger. If you had to talk about just IMFs, it's a larger atom, so you would have stronger LDs. So that can affect having to break those apart. Right, we're having to break them apart and get to a gas, so you have to overcome that as well. So if you had to talk about the differences in their IMFs, I does also have a stronger IMF. Predict which of the two processes, whatever, shown in the table has a greater change in entropy. Justify your predictions. Which one has a greater change in entropy? It's changing from the beginning to the end of disorder. I hope that you would agree that it's this one, because you're going from extreme order to disorder of a gas. The other one went from a liquid to a gas. This one's going from a solid to a gas. Solids are the most ordered. Liquids have a little more disorder, a little less order in them. And you can read it all. Should have the greater change in entropy. The sublimation of I2 may be thought of as a combination of fusion and vaporization. The conversion from solid to liquid would increase in entropy, as with the conversion from liquid to gas. It's only undergoing the liquid to gas conversion, so it will undergo smaller entropy increase. You don't have to say it all. I would just say it's going through two phase changes, going from extreme order to the same disorder versus a liquid only going to solid. I2S and Br2 liquid can react to form the compound IBr. Predict which would have the greater molar enthalpy of vaporization, meaning the amount of energy flow, IBr liquid or Br2 liquid. Justify your prediction. Again, let me say it one more time. I2 and Br2 can react to form the compound IBr. Predict which would have the greater molar enthalpy of vaporization. It would be IBr, and there's a couple reasons. About two must be given. First, IBr is polar, and dipole-dipole forces would tend to increase the enthalpy of vaporization, meaning there's attraction. You have to overcome that. Okay, again, you're having to overcome to enthalpy is flow of energy. Secondly, IBr should have stronger London dispersion forces because of the greater number of electrons. That's interesting. I didn't read the second part. I thought I read it as only one reason, so I stopped reading it. Well, either. Oh, there you go. Right. I wouldn't talk about the London at all. I would with the IBr. It doesn't have depth.
So in the first part it says that IBR is polar.
Well, maybe
The second
given.
one,
I swear it was most.
It's a stronger LD. Doesn't LD mean polar?
Everything has London. They're saying either one can be given. Everything has a London. So if you have dipole blows London out of the water. It's over. They're just saying these are some other things you could talk about. I know that's a little confusing, but everything has a London, even polar compounds. But the polar attraction is much stronger.
We made that little chart when we learned about this stuff.
Yeah, we did.
If it's polar, then it's dipole,
Or H bonding. Yeah.
and then if it's not polar, it's London.
Yeah. Yeah. Sorry. Shoot, I don't know if I want to get. Is this the last one or not? All right. Quickly, what this is basically saying is that you put two solvents on top of each other, H2O and C6H14. They're miscible, meaning they don't mix. Okay. That means that one's polar and one's not polar, by the way. Small drops of crystal are in there, in the test tube. They're purple. The C614 layer becomes light purple. What does that mean then? This is nonpolar, so is that. Like dissolves like. So while the H2O layer remains virtually colorless. Explain why the hexon layer is light purple while the water layer is virtually colorless. Your explanation should reference the relative strengths of interactions between molecules of I2 and the solvents, the reasons for the differences. Well, I just said it in a different way, but if you're nonpolar, then you don't have any charges, so you naturally will allow other non-charged compounds to dissolve in you, because if you have charges, you'll only be attracted to yourself. You won't be attracted to the solvent, because they don't have any charges. If your solvent has charges and you have charges, then you'll be attracted to the solvent. So there's a lot of ways you can say it, but like dissolves like. I mean, truly. But you'd have to explain it somehow. So basically, you dissolve in similar IMFs. If you don't have any charge, then you can float around in a liquid that doesn't have any charge. If you don't have any charge and you're in a liquid with charges, the liquid's going to be attracted to itself. It won't even allow that liquid to be mixed in with the dipoles or the H bondings. Okay, so you are going to have to find a way. You can read it yourself. There's more than that would be needed in here, but it's nonpolar, so those would have London dispersion forces, so they'd be more attracted, if you'd say a word, attracted to each other than water, which has H bonding. You have to have similar attraction forces for it to dissolve. Oh my gosh. Student then adds small crystals of Ki to the test tube. The test tube is corked and inverted. We'll just finish this one up, I guess. I thought we'd be able to get through more of these. The I ion reacts with I2 to form I3 ion, linear species. In the box below, draw the complete Lewis dot diagram. Hopefully you did that.
Is there any double bonds?
No. How would you have known how to do this? Guys, I is 7. 7 times 3 is 21, plus 1 is 22. If you just drew it all with single bonds, you would have had 20. Oh shoot, I need 22, so you should put another 2 dots on the top. In which layer, water or hexane, would the concentration of I3 minus be higher? Which one would it go into, water or hexane? Is this polar or non-polar? Maybe we're not sure.
It would be
That is sorry, this is non-polar, but it has a charge. I was looking just at that. This, because it has a charge, it's an ion. Ooh, I stopped myself right before I committed all the way. The ion itself has the charge. So when we have charges, we're attracted to other things with charges. Again, if it did not have a charge, by the way, I just want to point this out because this is where we're going to end. That would be non-polar by itself. But it's containing a charge. So the charge would be attracted to other things with charges.
So anytime anything has a charge, that makes it polar?
Or at least attracted to other charges. I guess I don't want to say the word polar. It has an attractive force,
So charge.
if that makes sense. Okay? Because then it's kind of like ionic. All right. We'll continue this tomorrow. Reminder, if you'd like to rent out a book to review, if you're not going to use it, don't grab it. But if you are, great. We have a couple things to stand tomorrow. Get your AP format in today.